This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. So you're running Kubernetes, probably leaning on a managed cloud service like AWS EKS, Google's GKE, or Azure's AKS for that sweet scalability and operational ease. But have you ever really dug into your network costs? A recent research paper suggests you might want to take a closer look, especially if your applications push a lot of data out to the internet. Get this. The study found that for certain network-intensive applications running on AWS EKS, that's Amazon's managed Kubernetes service, could cost a staggering 850% more in network fees compared to a comparable bare metal setup. 850%. That definitely caught our attention. The core issue highlighted by the paper, titled Kubernetes in the Cloud versus Bare Metal, a comparative study of network costs, is the complexity and potential expense of cloud network pricing compared to traditional bare metal hosting, particularly when dealing with applications that have high egress traffic. Egress just means data flowing out of the network, like serving files or streaming video to users. While managed Kubernetes on platforms like AWS offers undeniable benefits like rapid provisioning and reduced operational burden, the way networking is billed is fundamentally different from the bare metal world. On bare metal, you typically pay for network capacity. You might get a server with a 1 gigabit per second link included, or pay a fixed monthly fee for a certain bandwidth allocation. Whether you use 10% or 90% of that capacity constantly, the price often remains the same. You pay for the pipe. Cloud providers, however, operate largely on a pay-per-use model for networking. This sounds great for elasticity, but the pricing structures can be intricate. AWS, for example, charges differently depending on where your traffic is going. Traffic within the same availability zone. Think of a zone as a distinct data center within a larger region. Might be cheap or even free. Traffic crossing between availability zones within the same region incurs a small cost per gigabyte. But the real kicker is often the internet egress traffic, data leaving the AWS network to the public internet. This is typically the most expensive category, often charged at several cents per gigabyte. And unlike ingress traffic, which is data coming into the cloud and often free, this outbound traffic cost can add up very quickly for the wrong kind of workload. This complexity makes it hard for organizations practicing FinOps. That's the emerging discipline combining financial management and cloud operations to optimize costs. To get a clear picture, standard cloud billing tools often provide aggregated network costs for your whole cluster, making it difficult to pinpoint which specific applications are driving those costs. You might know you spent X dollars on data transfer, but was it mostly cheap cross-zone traffic or expensive internet egress from that one video service? So the researchers set out to create a methodology to directly compare these network costs under fair conditions. They wanted to answer, for a network-intensive application, is managed cloud or bare metal more cost-effective purely from a networking perspective? Here's how they approached it. First, they needed a representative application with high outbound traffic. Given that video dominates internet traffic, they chose Plex Media Server, a popular application for streaming personal media collections. This makes sense. Streaming video involves sending significantly more data out than comes in. Next, they set up 2 Kubernetes environments intended to be as identical as possible. For the managed cloud, they used AWS EKS. For bare metal, they used K3D, which is a lightweight tool to run a production-ready Kubernetes distribution called K3s in Docker, running on servers from a provider like OVH Cloud. To simulate real-world usage, they employed K6, a popular open-source load testing tool. They scripted a typical user journey, logging into Plex and streaming a video. This allowed them to generate controlled, repeatable network traffic patterns. Monitoring was handled by the familiar duo of Prometheus for metric collection and Grafana for visualization, standard open-source tools in the cloud-native world, allowing them to track resource utilization and, critically, network throughput in both environments. Now, a key challenge in comparing costs is ensuring you're comparing apples to apples in terms of performance. Cloud network infrastructure is heavily abstracted, which can sometimes affect performance differently than a direct physical network interface on bare metal. The researchers found that the amount of video data Plex downloaded could vary, so they used the Grafana metrics to carefully adjust the K6 load test parameters, like the number of concurrent users, in each environment until they achieved the exact same average data transfer rate. In their test, this was around 13 megabytes per second using 300 concurrent users. This step was vital for a fair cost comparison. They needed to ensure both setups were delivering the same service level. Interestingly, they noted that adding more users beyond 300 didn't increase throughput on their setup, suggesting a bottleneck elsewhere in the system, not the network link itself. With performance equalized, the focus shifted to cost measurement. For the bare metal side, the calculation is relatively straightforward. They looked at OVH Cloud's pricing. A server capable of handling the load included a 1 gigabit per second network link for a fixed monthly price, around $177 in their example. The paper notes that for bare metal, you need to dimension your network capacity carefully based on expected peaks. They adopted a common guideline of aiming for no more than 50% utilization of the network link at peak load to ensure performance doesn't degrade. This implies a degree of over-provisioning is necessary. Measuring the cost on the AWS side required more nuance, and this is where the open-source tool Kubecost came into play. Kubecost is designed to provide granular cost allocation insights within a Kubernetes cluster. However, the researchers point out that default Kubecost configurations might not allocate network costs accurately. They had to specifically configure Kubecost to understand the different AWS network traffic types and their associated costs. This involved defining which IP ranges corresponded to which availability zones to correctly identify in-zone versus cross-zone traffic. They also used a static IP for their NGINX ingress controller. That's a common component used to route external traffic into the cluster to reliably tag traffic passing through it as internet traffic. This careful configuration allowed Kubecost to break down the network costs accurately, attributing the right price, e.g., $0 per gigabyte for in-zone, 2 cents per gigabyte for cross-zone, 9 cents per gigabyte for internet egress in their AWS region example, to the specific traffic flows generated by the Plex application. So what were the results after running the load test for 30 minutes and extrapolating to a full month assuming constant usage? The bare metal setup cost remained fixed at the server's monthly price, covering the 1 gigabit per second link, roughly $177. The AWS EKS setup, delivering the same 13 Mbps throughput, racked up an estimated network cost of around $4,800 per month. That's where the startling 850% difference comes from. For this specific high-egress workload running constantly, the usage-based cloud network pricing, dominated by the expensive internet egress charges, was dramatically higher than the fixed capacity bare metal cost. Now, before you rush off to decommission your EKS clusters, let's unpack this. The paper is very clear. This huge difference is highly dependent on the application's traffic profile. The Plex streaming scenario is almost a worst case for cloud egress costs. What if your application has high ingress traffic, but low egress? Think about an AI service that ingests large video files for analysis, but only outputs small metadata files. Since cloud ingress is often free, the cloud model might actually be cheaper in that scenario. The balance between ingress and egress is critical. The researchers also considered applications with variable traffic patterns. Imagine that streaming service only operates for a few hours a day, maybe powering down components during off-peak times using cloud elasticity. Running the numbers, they estimated the monthly AWS network cost would drop significantly, perhaps to around $384. Still more expensive than the $177 bare metal in their example, but the gap narrows considerably. This highlights another factor, the utilization pattern. Constant high egress hurts on the cloud. Intermittent usage makes it less painful. This brings us to some important caveats and potential questions, which the paper acknowledges. Firstly, this study focused only on network costs. A real-world decision needs to factor in compute costs, storage costs, And crucially, operational overhead. Managing bare metal Kubernetes, even with tools like K3D, typically requires more SRE or operations effort than using a managed service like EKS, where the provider handles the control plane, patching, upgrades, and underlying infrastructure resilience. These operational savings with managed cloud services can be substantial and might easily outweigh higher network costs for many organizations. So the 850% figure is purely for the network bill in this specific scenario. The total cost of ownership comparison could look very different. Secondly, the benchmark used a constant load. What about highly bursty or unpredictable traffic? Here, the cloud's network elasticity offers value beyond just cost. On bare metal, you have to provision for the peak, meaning you might pay for idle capacity much of the time. In the cloud, while bursting might incur costs, you generally don't have to worry about hitting a hard capacity limit in the same way. For applications where handling sudden spikes is critical, the operational simplicity and performance assurance of cloud networking might be worth the premium. Thirdly, how sensitive are these findings to the specific providers? The study used AWS EKS and OVH Cloud. Network pricing varies between AWS, Google Cloud, and Azure, and different tiers or reserved capacity options exist. Similarly, bare metal pricing differs across providers. The exact percentage difference would likely change, but the fundamental pricing model differences generally hold. Finally, can you realistically apply this Kubecost methodology in your production environment? The paper demonstrates its use for analyzing a specific workload. Applying it accurately across a complex, multi-tenant cluster might require more sophisticated configuration. However, the paper provides a valuable blueprint for using open-source tools to get data-driven insights, at least for key network-intensive services. So what's the key takeaway for us engineers? Network cost, particularly egress, can be a significant, sometimes surprising, factor in your cloud bill, especially for applications shifting large amounts of data outwards. Managed cloud services offer immense value, but their network pricing models mean they might not always be the most cost-effective choice for every workload, especially compared to fixed capacity bare metal if network egress dominates. This research provides a clear methodology using tools like K6, Prometheus, Grafana, and specifically configured Kubecost to measure and compare these costs under controlled conditions. It empowers teams practicing FinOps or any engineer concerned with efficiency to make more informed, data-driven decisions about where to run specific network-heavy applications. It's not necessarily saying ditch the cloud, but rather understand your traffic patterns, measure your costs accurately, and choose the platform that makes sense for each specific workload. Remembering that network cost is just one important piece of the total cost and operational puzzle.